Okay, so this is where we go to, and I said that the most important thing is the one in red, the model, right? And then I showed you that. So if you define something like this, a model like this, model dot sequential. You see, sequential it means that we go from one layer to another layer. So the model is sequential, right? And then I said that the first layer is flattened layer, and then the input to the first layer is 28 by 28. That's where our image comes in. Our image for the MNES, for the MNES data set, the images are 28 by 28, right? So our input to the first layer is 28 by 28. And I said that normally what you do is that you take the images, a 2D image, right? 28 by 28. You want to actually flatten it and make it into 1D, something like this, right? So you flatten the 28 by 28 image into one, right? So it will be 28 times 28. It's about 700 and something, right? So now, so that is the first. That is the first layer. That's the first layer you see there. Flatten. That will flatten the 28 by 28 into one row, right? Then the next layer is called a dense layer. I explain why it's called a dense layer, right? I said that they have because they are, this is how the neurons are, right? And then the 20 there means that we have 20 neurons, right? And then this 28 by 28 image will feed into these neurons, right? Right? So the second layer is a dense layer because all the interconnections here are connected to those neurons. Everything is connected. That's why it's called a dense layer, right? Then the next one was another layer, another dense layer, which has 10 neurons. So the 10 there means that we have 10 neurons. And then that is the last layer. So we call it the output layer. And then these 20 neurons here are all interconnected to this 10 neurons here. So that one too is dense layer. So, and I said that we have 10 of this because we are doing the MNIST image classification. Then we have 10 numbers, 0 to 9. So each of them begins for 0 up to 9. And that's why we have 10 neurons over there. So that's just how the exams is going to look like, just as easy as that. Simple questions or something like this. So I would say that in the first layer, how many, then I told you that here we are when we are training, right, we are trying to find the weights and what? The biases, right? So I'll ask how many weights are in the first layer. Then you should be able to calculate that. We did that last week. So how many biases are there? How many total number of parameters are there? Stuff like that, right? In each layer. So layer one, how many weights are there? You should know how many biases. In layer two, how many weights? How many biases? In layer three, how many weights? How many biases? Hmm? Well, now you have done that, and then it's in the video. It's in the video already. Maybe. So if you go and check, you should see. Hello. Uh, Good evening. Fine. Pardon? Okay. Ah, yes, 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 yes. Yeah, I am already there. I have another class. Yeah, yeah, fine. Any of them that like, we do can. Oh, yeah. right? So I said you need to know how to calculate the weights and biases and stuff like that in each layer. And I've already explained that, right?
Okay then.
Okay. So now, so as
Why the creating the tension? For the 10, you have made it another because it's very key.
yeah, so here it is arbitrary. You choose it. So it's your choice. So maybe if you choose 20 and then you train the network and then you measure your accuracy. If the accuracy is too low, you have to come and change it to probably 40 or something, right? So you are experimenting.
For the 10 layer, yeah, you have to explain.
Yeah, that is it because of the number of outputs you have. That one is always fixed. But the rest, you can change anything you want. You can even add more layers. Instead of only 3 layers, you can add another layer, another layer, another layer. That's your choice. But you must know that once you are adding more layers, the time in training will also increase and stuff like that. So, right, so now, all you have done is this is exactly what you have done, right? You have taken your image, your 28 by 28 image, right? And then you have declared, as I said, 20 neurons in the first layer, and then you have 10 neurons in the outer layer, right? So this 28 by 28 will be, as I said, expanded into just one, and then fed into the first layer, right? And then the second layer fits into the last layer, and then stuff like that. So here, all you do is that if the number is 7, after you train it and then you give it, you give it the number 7. Once you have 10 outputs, right? One of them. So here, once you're using binary, right? It means that if the number is 0, the first one, if you give it a 0, right? The first neuron in the outer layer will be 1, and the rest will be 0. So if you give it 7, right? Means that the 0, 1, 2, this one here will be 1, and the 1 and the others will be zeros. That's all. And if you give it a 9, right, it means that the last neuron there will be 1, and then all the rest will be 0. That's how you know that it has been able to classify or predict the input you gave it, right?
So in this case, if it's written a 2-digit number,
It will work.
a 2-digit
No,
number.
it won't work. Or because you give it specific kind of data to train with. So once you give it that kind of data to train with, you need to feed it with those kind of data. Just one decade, one decade, one decade. If you give it 2 decades, it will mess up. It doesn't know it because you didn't train it with that kind of data. Understood?
Good morning, sir.
No.
In the US, just like
No, I think I've missed you. So,
No, what's that?
I think I've missed you.
Sir, this one, because it's 7, that is why the 10 is having the 1.
Yes, yes. Then if you give it a 9,
the last one.
it will be this one. This one will be 1. All the rest will be 0.
Then you use
So
the
8 means that the
Yeah.
other one
Because we are identifying from 0 to 9.
it's an easy working for you.
Yeah.
It's working for you. That's fine. You didn't know what the people do.
Yeah.
You say the thing has not been plugged. You just put it in the socket.
Okay, so the next thing is the next thing is there's something here called the activation function. I think I talked about that the last time too. Activation functions, right? So each neuron has an activation function, right? After, as I said, the neuron looks like this. If you take only one neuron, it looks like this. You have inputs, we have outputs, right? And then I said that, and then we have weights, and then we have a bias here, and then we have your input one, input two, input three, any of them. And I said that the calculation is that the output is equals to the sum of the weight times the input, right? Plus the bias, and then after that you pass it through a function. That function is called activation function. Simple as that, right? So now here we are using an activation function called ReLU, and it's a very important activation function. It's called ReLU. I think I explained that already. Or
This is called.
ReLU, rectify linear units. So what the ReLU simply is actually very simple. So you can explain it in your own way or define your own formula. What it does is that it checks. So we do the sum of the weight times the input plus the bias. Then we pass this one through the function, right? So if you do this calculation, this sum of weights and bias, and then the value is less than 0, right? What the ReLU activation function does is that it makes that value 0. Understood? If it does this calculation and then the calculation is less than 0, if it's negative number, it makes it 0. Now, if it does the calculation and then that number is greater than 0, then it maintains the number. So you can write your own formula for that, right?
So if it does the calculation, it gets 0.1.
And it gets 0.1, it's above 0. So it will keep it like that. So if it does, so probably we could say that the output is equal to, how will you define it? So the output, okay, if you have f of x, right? So this x is the w, this one plus what, and then this is the function. So f of x. So let's say your output y is equals to 0, right? If x is less than 0, and then your output y is equals to x if x is greater than 0. So you can just put it in your own formula, in your own way. So I think it is one of the questions. I've actually finished setting the question. So and then this one is one of them.
This is one of the questions.
Yeah, I say yes. I think it's what. Write the formula for the ReLU activation function. That's it. So you can just put it in your own way, but it should make sense in a sentence or in formula, or you can just say it's a maximum of. So if you do something like maximum of 0 and x, right? So it takes a maximum of 0 and x. So if the number is 0, then it will be 0. If the number is a negative number, it will take a maximum of 0 and that negative number, and then the maximum of 0 and any negative number is 0, right? So you can do it.
Is that right? The formula.
Rectify linear unit, right? So is that easy? Then our next one is so that is those ReLU are for dense layers, right? Are for dense layers. Now we have another activation function for the output layer, and then we have so many activation functions, and then here we are using what is known as the softmax. So the activation function for the output for this output layer is called what? Softmax. Have you seen it? So what does the softmax do? So here we have 10 outputs, right? The output layer has 10 outputs from 0 to 9, right? So now what the softmax does is that it calculates the probability that the number is a 0 and gives it a value, right? So it calculates the probability that the number is a 0, or the number is a 1, or the number is 2, or the number is 3, 4, up to 9, right? And then from that probability, you can know what the number is. So if you add up all the probabilities of the numbers, it should give you what? 1, right? So if the number is, let's say, 9, the last one, so it means that the last one will be around 0.99, and then the rest will be 0.000 something, 0.0. So if you add all of them up, you get 1, and then you will know that once you see the one with the highest value, it means that is what that is the number that was giving us input. So that's what the softmax activation will be.
I don't want to start up there.
Yeah?
I don't want to start up there.
I can't remember what it was.
Sam will do a recap class with us.
Oh, there's no recap after next week. That's all.
After next week.
Yeah, after next week I'm done.
So no examination areas.
No, no, probably.
I
not.
will read this.
So now the next is, so this is the code to actually compare, and then I think I explained optimizers and then loss functions and stuff like that in the last lecture. I said that when the machine learning paradigm is that you make a guess, right? Or I didn't explain this. You make a guess and then you calculate the accuracy or the loss, and then you optimize. It's all in the video, so you can go and watch it. So now here you have to use an optimizer. There are so many of them, but we usually use one called the Adam optimizer. And then we use the loss function to, I show you how to do the loss function and stuff like that. So here we are using the sparse, categorical, cross entropy. And then the metric is accuracy. We are trying to measure the accuracy. So you give it a number, and then you look at the accuracy. That's what we are trying to measure. Right? So, and then your last stage is model.fit. Very important. So this model.fit is what is going to start training your network. So you do model.fit, and then you give it your training images, then your training labels, and then you give it another important metric called the epoch 20. The epoch 20 means that you are doing 20 iterations, right? So now, usually when you take your training set, right, your training data set are always so many, right? And then you don't use all your training set to train your network, right? So what you do is that you break that training set. If let's say they are about 100,000, you break them into probably 100, 100, 100, 100, 100, 100, a group of 100, 100, 100, right? And then you use that one to train. You use 100 to train first. So that is the epoch. So if I give it epoch 1, it will just train for 1. It will use only 100 of the images and train, and then stop there. If I give it epoch 20, it will train for 20 times. It will use 100 random images and train. Then the next one, then it goes again, use another 100 and train. Use another 100, use another 100 and train and train and train until it gets to the 20.
By the epoch number. So we will be doing that quantity by the epoch number.
Yeah.
Said, is it like it will pick like the pockets of images?
Yes.
Or like all the images you have, it will pick them up and train them 20 times, or
No.
sample.
It takes a subset of the images.
Or something.
Yeah. So you use that one to train. Right? And then during training, you are always measuring your accuracy and then your loss. And then I said the last time that the loss always starts from a very high loss, and then your aim is that the loss must go near zero. Most of the time, it doesn't go to zero. It doesn't go to zero, but it must come down to around 0.00 something, right? And then that's when, if you are training and then you are evaluating your model, you will see some graphs like this. This is the loss, and if you see a graph like this, it means that your network is training well because the loss is always coming down. And then you have to also look at your accuracy. The accuracy must always be going up, right? So here we have an accuracy. It starts with accuracy of 0.88. That means 88% accurate. And then once you are training it with more data, the accuracy starts to go up to a point that it gets stable, and then that's when you know that your network has finished training. So most of the time it gets to around 0.96 or 0.98. So that's about 98% accurate. When you get to that kind of value, then you know that at least your network has done well. It has been able to get an accuracy of 98%. That's good, right? Then after that, you use what is known as the model.predict to predict some images. So after you train, you now give it some data that it has not seen before, and then see how it predicts those data. That's very important. You don't always give it, once you train it with some data, you don't always give it that data anymore because it already knows that data, right? So it's easy to classify that kind of data. So you give it another set of data, completely different, that the network has never seen before, and then it should also give you some kind of accuracy. So that accuracy must also be high. So if it has not seen some data before and then is able to predict, it means that your network has done very, very well. So here, let's say you try to predict a number like 7. So as I said, it is always the last layer will give you probabilities. So all of these are probabilities, right? If you see 2.449 exponent 09 means that 0.000000, right? So here it means that you are able to predict something like this. This is 9.99, so this is 0.999, right? It's the number 7. Once you give it the number 7, it will give this point to be around 0.99, and then you know that the number is 7, right? So I think I provided the notebook for that. Yeah.
So the 7
Yeah.
mark is the highest.
So I gave a Google Colab in the GitHub page. You can go and try it out. All the codes are there. Just run them to see how it works. Understood? Easy, right? Well, there is some playlists about how the whole thing is done, so you can go and watch them and you'll be okay. These are very, very easy concepts.